So now I'm going to begin a recording. Today is Wednesday. It is a little after 10 a.m. We are going to kind of continue our conversation about acids and bases. Now, what we're going to be getting into here is we will be tackling the strength of acids and bases. Um, and so, sorry, I'm working on one thing. So we're working on acids and bases and the strength of acids and bases. And what we need to do is really kind of decipher the differences between them. And a fair question to ask is, all right, well, Dr. Pepper is acidic, but so too is, hydrochloric acid. I can drink Dr. Pepper, but I can't and should not drink hydrochloric acid. What gives? Why? And one thing is the strength of those acids is what comes into play. Now, um, so on Friday, we're going to have some more top hat questions about acids and bases. We only have one question today, and I'll get to that, and I'll leave that open after a little while. But let's go ahead and get cracking. Present slides, start presentation, full screen. Strong acids and weak acids and strong bases and weak bases. So there's all spectrums or all parts of the spectrum for acids and bases. Some are strong, some are weak. And basically what makes them different from one another. Now, if you remember last time, what we talked about were a couple of different solutions. So we talked about sodium hydroxide as a part of Drano. We talked about ascorbic acid as vitamin C. Um, Sodium hydroxide, NaOH, is a base because it can accept a proton, whereas vitamin C can donate a proton. And that's kind of the definition that we're working with is does something or can something, let me rephrase that, can something donate or accept a proton? That's the question. If it can accept a proton, that would be a base. So accepting would be a base. And then donating is an acid. Now, if you remember last time, one of the other things that we did, we talked about basically concentration of acids and calculating, the pH of acids and bases for that matter. And their pH scale ranges from effectively 0 all the way to 14. So if something is, and then in the middle, we've got 7, which is neutral. So a neutral solution has a pH of approximately 7. And, we touched on this a little bit that the lower the pH, the more acidic. So I'm going to put acidic up here. And, this is a spectrum. So it's a range. So you could describe something as having a pH of 1, and you could describe that as being more acidic than something with a pH of 2. Then we've got basically anything above 7 all the way up to 14 is considered basic. So you can use these terms to describe different solutions. So a solution with a pH of 3. Okay, we can describe that solution a couple of different ways. I'm going to add some text boxes here so I can type it in. A solution with a pH of 3 is more acidic than a solution with a pH of 9. Okay, that's a true statement. Then another true statement these is less acidic than a solution with a pH of 1. Okay. And then last but not least, so we could say that a solution with a pH of 3 is more basic than a solution with a pH of 1. Okay, I want to highlight these last two items because we're doing a comparison of a solution with a pH of 3 and a solution with a pH of 1. So we're comparing these two basically, or these two examples of these two solutions, but we're using different terms for them. We're putting them in the context of, well, how acidic are they relatively and how basic are they relative to one another? So I want you to be comfortable and able to like read that sentence and say, yes, that's true, or no, that's not true. So a solution with a pH of 3, well, 3 is higher than 1, and therefore it's more basic. Then you can also say, well, 1 is a very acidic solution, so that's more acidic than a solution with a pH of 3. I think that's a helpful way to think about this, and I would expect exam questions and quiz questions kind of related to that. All right, now we proceed from here. These are your common, oopsies, jumped ahead. These are anions, and we've seen these in the context of our polyatomic anions. We had a part of this as nomenclature, and one thing that you're going to notice quite often whenever it comes to defining something as a base is you're going to look for and see OH minus. That's a hydroxide ion. So a hydroxide ion, which is what actually we saw over here, NaOH, sodium hydroxide. So one kind of rule that I've adopted over the years is anytime I see something hydroxide, chances are that's a base or a basic solution. Now, many times those are strong bases, but let's not go that far quite yet. Okay, now when we look um, when we look at formulas and names, that's where we can kind of decipher some common names for acids. So hydrochloric acid, whenever it comes to naming an acid, we say the ID, if you have IDE for the anion, so for instance, fluoride, that would be hydrofluoric acid. Another example would be bromide, hydrobromic acid, hydrochloric acid. So these are things that you've probably already done almost as like muscle memory and familiarity with HCl, but you haven't necessarily seen the rule for it. And so here's the rule. Now, bases are so much easier to name typically. Like I said, NaOH is sodium hydroxide. Now, when we look at these, which one of these is going to have our lowest pH? Well, our lowest pH is going to be our acidic solution, hydrochloric acid. Our highest pH would be our basic solution, or sodium hydroxide. So we played around with this the other day as well, where we were looking at the concentration of H3O plus and hydroxide ions. Now, one thing that I want you to take away from this is that H3O plus is the same effectively as H plus. So anytime you see this, don't get overwhelmed and think, oh no, it's totally a new thing that I have to learn. Nope. Think about H3O plus as being analogous to or the same as effectively H plus. Now, let's go back to this because I want to play around with this a little bit more and think about different solutions. So what we've got is at the, no, that's not the one. I want the micro level. Okay, so here we have a solution with a neutral pH. So a pH of 7. So that's a neutral solution. And what I want you to look at is the number of hydrogen ions and hydroxide ions. Add to the chat what you notice about those two numbers and what you notice about those two numbers in comparison to one another. I'll give you a little bit of a direction. Those are small numbers. What do you notice about them? Well, 1.0 times 10 to the negative seventh is our concentration of what are known as hydronium ions or hydrogen ions. And 1.0 times 10 to the negative seventh is our concentration of hydroxide ions. And if we look at, in addition to that, our level here, on that scale, that's intentional. The concentrations of those are equal to one another. So basically, the amount of acid that is in that solution is equal to the amount of base. So with maybe you've heard this term before, but if you spill an acid on the ground, what do you do with it? Or what do you do? I mean, you could wipe it up, sure, but is there a chemical term that maybe you've heard before, starts with an N, that you're going to want to do to kind of treat that acid? I'll give you another hint. It starts with an N and ends with a neutralize. Yes, yes. You guys got that in before I said N and neutralize. So absolutely right, Savannah and Caitlin. So you want to neutralize that. And so effectively what you could do looking at this is you could say, well, however much acid is there, this 1.0 times 10 to the negative seventh, that is neutralized by the exact same amount of hydroxide ions. Okay. Now I want you to focus on those two and do not worry about this water. I'm just going to put a blue box over that, so don't worry about that. Now, let's go ahead and I'm going to ask you a question. If I make this solution more basic, so if I have my pH go up, what do you think is going to happen to the level of this that I've just highlighted? Do you think it's going to, in my to give you some parameters, do you think it's going to go up, down, left, right? If I'm increasing this right here, and looking at our scale, we've got 10 to the second. That's a big number compared to 10 to the negative 16th. Corazon, okay, so if my hydroxide goes up, then the hydronium ions, the H plus, that's going to go down. Okay, so if I go to a higher pH, so let's watch that. Thank you very much for answering and offering that up. Let's see. Let's go ahead and add, how about some, let's just make it a, let's see, not vomit, spit, water, soda pop, milk. No, milk is fairly acidic. Drain cleaner. There we go. Drain cleaner. Our Drano. Our pH went up to 13. And our hydroxide ion concentration went up as well. So when you think about an acid or an acidic solution and a basic solution, one way that you could think about it is, let me add this, a basic solution I guess you could say like the hallmark of a basic solution is, what's my present? Um, is a high hydrogen or hydroxide ion concentration. So high, or let me rephrase that. Higher OH minus. I'm going to put these brackets here. That bracket indicates concentration. Higher hydroxide ion concentration than H3O plus concentration. So my hydroxide ion concentration is higher than my hydronium ion concentration. which again, just to avoid any confusion there, I'm going to go ahead and rather than write H3O plus, I'm going to write H plus here and H plus here. Okay. Is everyone good with that? Now, let's go ahead and refresh this. Start back at a neutral solution. And based on what we just did, let's clear this and let's go with battery acid. Okay. What do you think the pH is going to do as soon as I select battery acid? Do you think it's going to go up? Do you think it's going to go down? Or do you think it's not going to change? If I select battery acid, do you think battery acid is going to have a low pH or a high pH or a pH of 7? So I'm asking, like, is it lower than 7 or higher than 7? That's my question. Caitlin, you're absolutely right. So I'm going to select battery acid. Okay. Whenever I do that, let's watch the hydrogen ion concentration or the H3O plus. That goes way up. The hydrogen ion concentration in an acidic solution is higher than the hydroxide ion concentration in that same solution. Now, are there both hydrogen ions and hydroxide ions in that solution? Yes, there are. So they are both there, but when you compare the two of them to one another, this hydroxide ion concentration is so low that it's almost at a level that it's kind of forgettable or negligible. This is such a low concentration, whereas this H3O plus is a relatively high concentration. And I always like to use the terms relatively because then you can, that gives you a comparison. You're comparing your hydrogen ion concentration to your hydroxide ion concentration. I'm going to clear all my drawings out. And now what we're going to do is we're going to go back here to where we were. Okay, so that's one of the things that I want you to be able to do whenever we look at a solution. I want you to be able to, last time we played around with and calculated what is the pH based on the hydrogen ion concentration, but I want you to also be able to tell me, well, what's higher, the hydrogen ion concentration or the hydroxide ion concentration based on the pH? Expect a question like that on, a quiz or an exam. Okay, so when we look at these solutions, we've got our neutral solution. Actually, I'm going to go ahead and do that. Okay, so add to the chat. Which one of these solutions do you think is acidic? And I know that it just popped up on the screen, but let's imagine that it's not there. 1, 2, or 3 is acidic. And I'm going to, okay, we got cortisone answers. 3 is acidic. Okay, so I'm going to follow along with that. If we look at all of our legend over here, we've got hydrogen ions, we've got potassium ions. Oh man, we haven't really talked about potassium ions, but well, oh boy, is that a problem? Then we've got NO3 ions or nitrate ions, and then we've got hydroxide ions, which if anyone's ever played Mario Brothers, that kind of looks like the little mushrooms that you get in Super Mario Brothers. Okay, but we want to look at this and say, well, what is there a greater concentration of? Effectively, what we're comparing is our hydrogen ions and our hydroxide ions, because those are the two that we're interested in, and those are the two that we kind of care about more than any others. So whenever I look at that, I'm seeing that, all right, well, we've got, I'm going to use this tool. Yeah, there we go. Hydrogen ion, done. Okay, there's 1, 2, 3, 4, 5, 6. Okay, so I've got 6 hydrogen ions. How many hydroxide ions? I'm going to switch colors. I'm going to go with light purple. 1. What do I have more of? Well, I've also got nitrate ions, but if I'm just comparing my hydrogen ions and my hydroxide ions, well, Corazon, you're absolutely right. What do I have more of? I have more hydrogen ions. And when it comes to determining if something is acidic or basic, those hydrogen ions and those hydroxide ions are the ones that we care about. So there we go. H plus and OH minus. I've got a 6-to-1 ratio. Now, this specific ratio is not super important, but it is worth noting that, well, I'm going to go ahead and give myself a little note here. More H plus than OH minus. So, put a parenthesis there, acidic. Now, if we look at my middle solution, I've got 1, 2, 3, 4, 5, 6, 7 hydroxide ions. And then how many hydrogen ions? 1. So I've got more hydroxides than hydrogen ions. So that means that this middle solution, number 2, is going to be basic. And then looking at the first one, we got 1, 2, 3, 4, 5, 6 hydrogen ions. And then we go to, I'm just going to go to this. 1, 2, 3, 4, 5, 6. Get the same number. So if we were to assign a pH to each one of these, really what we would do is say number 1 has a pH of approximately 7. Number 2 has a pH of, let's go with 10. And then number 3 has a pH of, we're going to call that 4. Now, you could argue that, oh, well, I think it's 3 rather than 4. Sure. Okay, that's fine. But that's not really we're on the same page and we don't need to get kind of lost in the details there. Okay. Now, our next classification is that we want to look at the ions in a solution and the conductivity of a solution. So we've already talked about these with respect to like electrolytes and solutions that are capable of conducting electricity, like sodium chloride. A saltwater solution can conduct electricity. But let's go ahead and not that one. There we go. There it is. Purples. Okay. So if we put these electrodes in, well, we have an equal number of hydrogen ions, H3O plus, and hydroxide ions. Now, if we are to, let's say, add an acid, we've got lots of hydronium ions, and we can therefore conduct electricity. Okay, so now let's reset that. Let's go back to the light, and let's ask the question, if an acidic solution, so our takeaway from this is that an acidic solution can conduct electricity. We had HA, that was our strong acid. That conducts electricity super powerfully. What about a weak acid? Oh, lo and behold, what happened? Well, the intensity of our light went down. So strong acids conduct electricity very strongly. Weak acids are not, as you can imagine, not as strong. Now, all right, let's go with a strong base. What does that look like? Oh, a strong base can conduct electricity. Let's check out a weak base. Oh, a weak base and weak acid. The intensity of the light is basically staying the same. So if we were to kind of get a summary of this, or kind of summarize this thought, well, acids and bases conduct electricity. And they conduct it well. Okay. But the strength of those acids and bases, the stronger acid and the stronger base conducts electricity more strongly. Now, the difference between those, let's think about this on a molecular level. Okay. When we have a neutral solution, we've got an equal number of these and these. So if we were to count them up, it'd be 1, 2 hydroxides, and then 1, two hydrogen ions. Okay, so those are going to be balanced. Now, if we go to a strong acid, let's check out a strong acid. Oh, this is kind of overwhelming. Now, if we count all those up, what we're going to notice about that count is that we've got a lot more of this. We got a lot of that. What is that? That's an ion. We've got a lot of ions in there. Then let's look at a weak acid and let's look at the equation for a weak acid. Okay, well, oh, stop the press. Let's rewind for a second. Strong acid. I want to draw your attention to this arrow right here. And then a weak acid. Well, in a strong acid, that arrow goes in one direction. A weak acid, by comparison, it goes in two directions. So what does that tell you about, your products and your reactants? In a strong acid, you have more products than reactants. And in a weak acid, you kind of have not necessarily an exactly equal number, but comparable numbers of products and reactants to one another. And the more products that are formed, the more ions that you get. So if you're to look at this and say, well, what's an important takeaway? Well, first is that acids and bases both conduct electricity. Stronger acids and stronger bases conduct electricity better. The more ions that are in a solution, the better you're going to be able to conduct electricity as well. Now, I'm going to clear all my drawings here. And I'm going to go back to where we were. Okay, so what we were kind of looking at here and what we wanted to get from this was a thought about ions and numbers of ions. And a important item or an important detail is that, well, oopsies, strong acids make more ions than weak acids. So when you think about the strength of a acid or a base, and I'm going to add below that, strong bases make more ions than weak bases. So if an acid or a base is strong as opposed to weak, you're going to get more ions in that solution. When you get more ions in that solution is a better conductor of electricity. Now, here what we have is that same sort of idea, but it's explained a little bit differently. In particular, we're using this term ionizes. So a strong acid or a base will ionize completely. And a weak acid or a weak base will only ionize slightly. So one of the ways that I always try to think about classifying a acid or a base, or a strong acid or a strong base. Let's go ahead and I'm going to use this notation of HA. Now, HA is an example of a kind of the term that we use as a general acid. This will break down into H plus and A minus. Okay. Now, if HA is strong, it will completely ionize. So my question for you is, and I want you to add to the chat, if HA is a strong acid, let's say that we have 100 molecules of HA that will completely ionize. How many H will we have? And how many A minus will we have? And we're starting out with 100 HA. And then actually yeah, that's what we got. We start out with 100 HA. if this molecule will completely ionize, and just to bring things back, H plus is an ion and A minus is an ion. If somebody add to the chat, how many H and how many A will be present when you add HA to water? Well, it's going to completely break apart. So when it completely breaks apart, we're going to end up with 100 H plus and 100 A minus, because this HA will totally separate. Every single one of those molecules will separate into our two separate ions. Now, that is kind of the definition for a strong acid or a strong base. So now let's put this in the context of a strong base. NaOH, sodium hydroxide, is a strong base. Now I want everyone to add to the chat. If you start out with 50 NaOH and you add that sodium hydroxide to a solution, how many Na and how many OH minus, right? Na plus and OH minus will be in that solution. And let's just, whenever the reaction's done, how many will there be? That's my question for you guys. Haley, you're absolutely right. Alyssa, that's a great, I'm happy that you answered that. We're going to end up with 50 Na plus and 50 OH minus. That's a great contribution, Alyssa. Thank you very much. Because of the fact that, I know that that's the sort of answer that I gave the first time I had this question, because I'd be like, oh yeah, there's 50. And so it's going to be split into 25 and 25. But let's think about what one NaOH is. And NaOH is one complete molecule. And whenever that complete molecule is broken up, well, this one thing splits into two different parts. And if there are 50 of these right here, then you're going to end up with 50 Na plus and 50 OH minus, because they came together to make that one NaOH. Now, a weak acid or a weak base, well, it's going to only ionize slightly. So when you look at a weak acid and a weak base, let's say that I'm just going to again label HA for my acid. And a good example of a weak acid is something that's going to go back and forth. So when you add that weak acid, you're going to end up with H plus and A minus. So the products don't change, but the abundance of them does. Now, if we were to, let's say, I'm going to label this as I, or initial, and then F for final. Okay, so if we had HA initial, we're starting out with, let's just say 100 molecules of HA. Okay, then what we're looking for is, well, our final. After this reaction's taken place, we've got HA, that's reversible, H plus A minus. What do we got? Well, this is where we only partially digest, or not digest, I'm sorry, partially ionizes. In which case, we're going to end up with 90 molecules of HA. So now my question, and if somebody gets this right, yeah, I'm going to do this. If somebody gets this right within the first, let's say, three answers, the three contributed answers, that's a bonus point on the next test. One bonus point. I'm going to make a note right here. And just a second. Okay. So we've got 100 molecules of HA. This is a weak acid. And that weak acid is going to partially or slightly ionize, such that we're going to be left with 90 HA. My question for you is how many H plus and how many A minus? So basically, what is going to, and let me go ahead and put this in here, 0, 0. So my question is, what number goes in here and what number goes in here? And if one of the first three answers is correct, that's one bonus point on the next exam. No, just regular. Add it to the chat. Okay, now stop. Is not 45. Okay, so the first thing that we want to do is we want to think about, we started with 100 HAs. And after this has taken place, so this is our final. Now we have 90 HAs. So let me give you a little bit of a picture. I'll give you a simpler picture. Okay, so we've got, I'm going to go with, yeah, okay, 5, 6, 7. Okay, so that's 5, 6, 7, 8, 9, and 10. Okay, now I'm going to add blue. Okay, so what we have is, so imagine HA is these molecules right here. Okay, so there's my 10 HA. And I'm just going to simplify my numbers. We've got 10 HA. Okay, so this is our initial. Is everyone good with that? We've got that, and we throw it in water. And we let that kind of simmer, let that incubation take place, let that reaction take place. And then this is our final. Okay, so I am working in the lower right corner. Okay, so there's my initial. Now, after the reaction has taken place, what's different? Well, 9 of those remain intact. So I'm going to get rid of this. So if 9 of them remain intact, which is similar to my 90, then what happened to the last one? The last H and the last A? Or how many of them, how many free H's, how many blue balls and how many red balls are in that solution is my question. Okay, so these, the combination, we've got 90 of those red and blue balls together. 90 of those are still, those remain intact. That molecule stays together. But then what we've also got is one free and one of these free. So this would be my A minus, this would be my H plus. So I started out with 10 of these, and my final 9 of them are still together. The remaining ones, well, the remaining 10, if we look up here, well, those remaining 10 split up So that means I've got 10 H plus and 10 A minus. So let me clear out some of my drawings here. Actually, I'm just going to clear all this page. So I this is we're going to just go through a couple of examples here because between a strong acid and a weak acid, that's one of the most important things. Okay. And with that said, I did not give you three answers because we worked through that last one together. So I'm going to throw that bonus point on there. Okay. Now, so we're good there. But I want you guys to be contributing answers to this. Okay. So we've got a strong acid. Now, that strong acid, let's just go ahead and I'm going to call it HA. And this will go in one direction and it will break up into H plus and A minus. Give me a number of how many molecules of HA that I have. Just any number. Perfect. We've got 100 copies of HA. And that, let's imagine that that's a solid. Whenever I add that to water, since this is a strong acid, it will completely ionize or completely dissociate. So imagine that my right and left hands are coming together to make HA. So I've got 100 combos of these. Every single one of these is going to separate. So I've got 100 copies of this, and they will all separate. Now, when they separate, this is H and this is A. How many H's and how many A's do I have when a strong acid is put into water? And I'm going to erase this 100 because that's what I started with. 100, you're absolutely right. So I'm going to end up with 100 H pluses and 100 A minuses. So think about, I think that a good way to think about this is that you have an acid that's made up of two parts, and you have lots of them. You have hundreds of copies of those compounds. And when you put it in water, those compounds come apart. Do you still have those pieces? Yeah, those pieces are floating around in the solution. If you had 100 HAs, now you have 100 H's and 100 A's. That is an example of a strong acid. That's what a strong acid does. It completely separates. Okay. Now, it's kind of like if, yeah. Then we've got a weak acid or a weak base. Okay. So a weak acid, I'm going to label that also as, well, HA. And here we've got 100 of this HA. These will not completely dissociate. Only about 10% of them will dissociate. Only about 10% of them will separate. H plus and A minus. Okay. Now, when only about 10% of them separate from one another, actually, here, we'll do it kind of stepwise. We started with 100. Our first HA is going to separate. So that first HA is no longer there. So now we're down to 99 HAs. My question for you guys is how many H's and how many A's are there? In that solution? Because I'll give you a hint, there's 99 HAs. So how many free H's and how many free A's are there? Perfect. 1 and 1. Okay. So now let's go, and another one is going to separate. Now we've got 98 HAs. What's my number of H's up to now? Okay. My number of A's is also up to 2. Perfect. Okay, so now I'm going to erase this. And again, we're starting out with, let's say that we've got 100 copies, 100 weak acid, 100 HAs, and we add it to water, and we've got this is a bit of a jump, but you shrink yourself down to the atomic level and you're floating around and you count up and you see 75 HAs. How many H pluses will you see and how many A minuses will you see? 25. Perfect. 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 That is absolutely perfect. Okay. That is like the fundamental part of a weak acid compared to a strong acid. The same thing goes for a weak base. Okay. Now, let's go ahead and look at an example. I'm going to switch this up a little bit. We'll see. Alyssa, that's a fantastic question. You'll see a question, you'll have like a kind of word problems that go with that. Or, if I were to say in a solution, think about it like this. Here, I'm going to draw a beaker. You've got HA, H plus, A minus, HA, and maybe I draw like a little circle over it to make it kind of favorable. You've got that, 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 and that. Okay. So I'm happy that you asked that because this right here, that beaker that I just drew, my question for you is this like this, think about this as this solution's been made. It's there. Is this a weak acid or a strong acid? And I'm going to stop talking so you guys can answer it. But now I'm going to add in a weak acid, you will start out with, or you will see HA, H plus, and A minus. Those three will all be there. So you could think about it as if I'm looking at a solution, absolutely, Alyssa. If I see HA and H plus and A minus, that is a weak acid. Now, if I am given the same thing and I look at a beaker, I'm looking for HA, H plus, and A minus. Now, if I do not see HA, if I do not see that HA, I only see H plus and A minus. So if you were to see something like this, H plus, A minus, H plus, A minus, is that going to be a strong or weak acid where I just kind of haphazardly drew part of a star? Absolutely. Great job, everyone. That's fantastic. Wonderful. Fantastic. That's great. Okay. So when you think about a strong acid or a weak acid or a strong base and a weak base, you need to think about it as, well, how much does that acid or base split up? Does it split completely or only partially? If they split completely, if every single one of those molecules, as soon as they hit water, they split up completely, that would be a strong acid or base. If only some of them do, that would be a weak acid or base. So think about it like, is the molecule intact in solution? If the molecule is intact in solution, so like we've got HA here. If I look at my solution, I see HA in there, that's a weak acid or where that would be a weak acid. I mean, basically, if you're looking at any solution, you're like HA, A plus, or A minus or H plus. If I see HA, my first thought is weak. If it's not there, strong. So we're going to keep, I got a direct message from someone, and we do have class on Friday, and we'll be talking about this again on Friday. And then this upcoming Monday, it's going to be a pre-recorded lecture. And I think that we might be through acids, but uh, strong and weak acids and strong and weak bases and everything like that. Um, but anytime that you have questions about this, by all means, contact me. I'm going to be, your quizzes, there will be some questions about this on your quizzes that will be due on Sunday. So play around with this and, I'll give you questions where I show you, here's a beaker. What is this? A strong acid or weak acid? Strong base or weak base? But yeah, we will continue talking about this. In the meantime, though, I'm sorry, it's 10:51, so I've taken too much of your time. I'm happy that we spent time on this because this deserves it. It needs it. Um, no, I'm sorry, Amira, we have one more exam, and that I believe is December 4th. That will be our fourth exam on the last day of class, and then we'll have our final, I think it's on the 8th or 9th. Um, but that's what I got. I hope that you guys have a great Wednesday, a great Thursday, and I will see you on Friday morning. Okay. I just wanted to
You as well. Thank you.
thank you guys.